Hello, this is a Chai on Science and Society, and our guest is Dr. Ryan MacDonald. He is right now a NASA Sagan Fellow, so my favorite type of fellow uh, because of Sagan, and he's at University of Michigan. But he is soon moving as a lecturer position at University of St Andrews in Scotland, and perhaps being in the US, this may not be a bad time to get out of here. So welcome, Ryan.
Thank you very much, Salman. Great to be here.
So I thought you would be a perfect person right now to talk about the big news for the last roughly 2 weeks that has dominated, and that is about a potential discovery of biosignatures. And I'm using the word potential in a deliberate way, around an exoplanet K2-18b, which, just to summarize, just for people to get sort of like, caught up to it, it's about 100, it's a star. Which is smaller than our sun. It's a red dwarf, which is about 120 light years away. This particular exoplanet is about 9 times mass of the Earth. Its radius is about 2.5 times the size of the Earth, but it is in the habitable zone, and it goes around its star about 33 times, 33 once every 33 days. The paper that came out, led by a team at Cambridge University by Niku Madhusudan, and the paper claimed that maybe it has detected some sort of biosignature. So, you are an expert. Your whole work is your research focuses on um, exoplanet atmospheres, also looking at from data from James Webb Space Telescope and modeling, something that this group has also done. So I wanted to hear what you have to say and how do you think about this discovery. So first of all, I'll just get a sort of like very basic response to it. How do you see this claim about the detection of a potential biosignature from K2-18b?
The first thing that I will highlight is just to make clear kind of how we're actually doing these measurements. What we're doing is we're observing a planet when it passes in front of its star, light filters through the atmosphere, and then we essentially look for how the amount of absorption of starlight changes with color or with wavelength. And then by comparing that to theoretical models, we can conclude which potential gases could actually be present in the atmosphere. So K2-18b has had like a long and storied history. Actually, the first time we detected its atmosphere was even with the Hubble Space Telescope. Back in 2019, it was reported that water vapor, steam, had been detected in its atmosphere. But these are very hard measurements to make for small and cold planets like K2-18b. This is not a rocky planet. This is something in between Earth and Neptune. We call it a sub-Neptune because it's kind of halfway in size between the Earth and Neptune, which is 4 times the size of the Earth. So this is a class of planets we don't have in the solar system, and that makes it kind of hard to do the analysis because we don't know exactly what to expect theoretically. So when trying to explain spectra that we obtain of such a planet with the James Webb Space Telescope, we have to test a wide variety of different possible molecules that could be present to see what ultimately fits the data the best. So I mentioned just now that we first thought there was water vapor in the atmosphere from Hubble. Then the first JWST data came down in 2023, and we found actually we were wrong. It's not water at all. It was actually the molecule methane that looks similar to water at a certain wavelength, but with enough data over a wide enough wavelength region, you can distinguish between the two molecules better. So already we had an example of a molecule that had been claimed at 4 sigma significance, so very high significance, that turned out not to be real. It was actually methane. But that's good. We learned more about the planet, and methane is something we expect to see in cold gas giants. We see it in Neptune, we see it in Uranus. That was something that was for sure. So we know that K2-18b is a hydrogen-rich atmosphere based on its size and its mass. And we're pretty certain that methane is present in the atmosphere. we've done an independent reanalysis of that first JWST dataset and confirmed that the methane is real. So that's what we know so far to set the stage. But any other chemical species, in particular molecules like dimethyl sulfide, which is the potential biosignature that is going around in the news at the moment, these are incredibly hard measurements to make. They're weak signals, and not only are they weak, there are a variety of different molecules that have similar shape absorption at the same wavelengths where dimethyl sulfide absorbs. And so my first take on this, given the historical context of how methane was mistaken for water, is, are we actually sure that it's DMS? And for that, you need to dig into the statistics of how confident it is that there's any bump at all. And then even if there is a bump in your data, you have to make sure that you test enough alternative explanations to really know that you're seeing that molecule, and there isn't something else in the atmosphere that is masquerading as dimethyl sulfide. So
So,
there's a
so
lot of tests that need to be done.
so Ryan, if I can go back to a
Hmm.
little question. I mean, you mentioned that where it was water vapor, and it turns into sort of like, that was likely methane with James Webb Space Telescope. So one of the ideas behind potential life there on K2-18b, or why it becomes interesting, is what, in fact, the same group actually called them Haitian worlds, like hydrogen rich and ocean worlds. So, is that particular idea that this exoplanet may have an ocean, is that been thrown out, or is that something under debate, or how does that particular aspect, how does that come in, because that features into the idea that there may be a biosignature because there is an ocean
Hmm.
over there. So is the ocean claim, does that still exist?
There is a very active and vigorous scientific debate about the nature of the interior of this planet. The group in Cambridge that has been, doing a lot of the work to obtain these JWST observations favors the ocean scenario. The main argument that they use in favor of this is the methane that is present that we've confirmed, but they also say that because the gas ammonia, NH3, is not detected, that the ammonia is essentially kind of absorbed into a liquid water ocean. However, other researchers have noted that if you have a magma ocean underneath the atmosphere instead of a habitable liquid water surface, ammonia can dissolve into magma equally well. So at the moment, the water world Haitian scenario is a viable explanation, but as is a magma ocean underneath a layer of hydrogen, or even just a scaled down version of our own Neptune, a gas dwarf, if you will. And that is something that is also consistent with what we have currently measured. So we don't know is the honest answer, but that's exciting. And we can design follow on observations to actually test the predictions of these different theories to ultimately figure out what this planet is like.
So we get sort of like, okay, so there is a debate about that. We're not sure. Okay, so let's get to the reason why, in some ways, this paper got so much attention was that there is a potential, and I know you have written about it too on Blue Sky as well, about 3 sigma detection, because there is some argument about, like, that the paper claims that there is a 3 sigma detection of dimethyl sulfide. And even though the authors actually themselves claim that 3 sigma is not what is considered as a strongest evidence, we need a 5 sigma. But you have reservations even regarding the 3 sigma detection. So can you elaborate that, because that's a
Hmm.
pretty important sort of a
Yeah.
context.
Yeah, this is really important because what has been kind of doing the rounds are
Yeah.
claims that the probability that DMS or this related molecule, dimethyl disulfide, is not present is 0.3%, which is what intuitively you would expect for a 3 sigma detection. But if you take the numbers in the paper itself, they calculate something called a Bayes factor, which is how much more likely is it that the molecules are there relative to them not being there? And the number is about 2.5 times more likely if you consider a wide variety of like 20 different molecules that could be present in the atmosphere. But then what they do is knock out most of the molecules besides four: methane, carbon dioxide, DMS, and DMDS, which essentially is assuming that half of the data, so the data with colors that have wavelengths longer than 9 micrometers, can only be fit by these two possible biosignatures, DMS and DMDS. And that essentially forces the model to put them in because it's the only considered explanation for half of the data. And when you do that, you increase the likelihood of them being there from being 2.5 times more likely to about 25 times more likely. And that would be roughly intuitively a 2 sigma detection. And then they use kind of some formula to map this 25 into an equivalent sigma value, and out pops the 3 sigma. But I think the most intuitive thing is that from the numbers in the paper itself, when they test a wide variety of different chemical species, the false probability rate is about 28%, not the 0.3% that is being stated. So it's what many other fields of science would consider to be a 1 sigma detection, not the 3 sigma that is doing the rounds. And we don't use the word detection for a 1 sigma thing. They vanish all the time. I've had 2 sigma results in my own research that have completely vanished when we got other data sets or revisited it with a different technique. So ultimately, this is not a result that we should be using the word detection for, because that instills a much greater level of confidence than what ultimately the data is actually showing.
So if I understand it correctly, basically when they were looking in the models, what they were placing in for in the infrared regime, they only used those two molecules, whether their presence makes a difference or not, but not other possible molecules that could have come in and also may have shown their detection and diluted these two particular molecules. Is that what's going on, if I
They
understand it
they
correctly?
they do a two-step thing. They start by considering 20 different molecules, which is great.
Right.
That is exactly what you should
Right.
do. And it's kind of like hidden in the middle of a sentence somewhere that they find this very low significance. They say it's 2 sigma, which is equivalent to
Right.
the 2.5 times
No,
more
no
likely.
detection.
Then they throw out 16 of those
Ah,
molecules and redo the
I
analysis.
see.
And that's where they get the 3 sigma values that they end up quoting.
I see. So, okay, so that's, I mean, obviously that's problematic. So I'm just curious, where do you have you gotten a chance to look at their observations or to run sort of like the models on their observations, or if not, when are you going to get a chance, and are you
Mhm.
going to do that?
So the raw JWST data is not publicly available yet. It becomes available automatically 1 year after the observations, which in this case, because they were observed in April of last year, is very soon. A couple of days from now, the data will become available. So some astronomers will be looking at the raw data. Others are just taking the data, the processed JWST spectrum from the paper, and running their own analyses on it. So we have already reanalyzed the previous JWST data for K2-18b. We actually had to wait 9 months after the publication for it to become publicly available. And we then spent many, many months from scratch reanalyzing it. And what we found is the methane was real. That was confirmed. Great. But the claims of dimethyl sulfide from the last paper in 2023 did not stack up. There was a non-detection. And we also did not see carbon dioxide, which had been claimed as a 3 sigma detection. So that's a pretty big deal, and it kind of shows how something that you're calling 3 sigma can vanish when you do a completely fresh reanalysis and very carefully look at the data and the statistics. So what I can say is there are a lot of conversations going on behind the scenes of different astronomers that are planning reanalyses, starting at different stages of the data. So you can certainly expect that claims of this magnitude will be very carefully analyzed, especially because when other teams like our own have looked at the previous data, many of the claims have not panned out.
All right. So towards the end, I would ask you, okay, so I'm assuming that they will get more time on JWST to look at K2-18b, and I think that probably is going to be justified because of the fact that it is interesting, and to see whether follow up, whether which way it's going to go. So I'm curious, especially regarding dimethyl sulfide. Do you think so? What would, how would you, or do you think that that would, if its detection does pop up over 5 sigma, let's say, um, first of all, do you think that might be the case? This is not the case right now, but from what you know about the system, do you think that there is a chance that it might be there? And secondly, where would be your step in terms of, you say, well, here are these biosignatures that you might think, I can say like this is interesting. Probably there is um, life there.
So, personally, I think there are so many assumptions that you have to make in order for there to be a significant dimethyl sulfide abundance in the atmosphere. Firstly, you have to say, okay, the amount of irradiation the planet absorbs is just right, and the amount of light that the planet reflects from its albedo is just right for there to be a liquid water surface under the atmosphere. If it's ever so slightly too hot, the water becomes supercritical or becomes a magma ocean, and then there's no life. So the planet has to have the right nature. Then you have to assume the planet has life. And then you have to assume that the biological flux, well, you also have to assume that the life produces DMS. It could be something completely different. And that the amount it produces is enough to be detectable. There's so many assumptions that you have to make that personally I don't think that the dimethyl sulfide will ultimately turn out to be real. But ultimately, astronomy is a data-driven field. If we continually get better data, more and more observations with the MIRI instrument, only a single observation was presented in this new study. If we get 5 or 10, which would not take that much time on the telescope, and then we see statistically there is a large bump around these wavelengths, that alone would be incredibly exciting, and we would have to then do the very careful work to check if it can only be DMS or if there are other possible explanations. And so that would be incredibly exciting. And personally, I really hope that there are some spectral bumps and wiggles and weird things that we have to explain. Because ultimately, that's where the science takes place. And this is my bread and butter, like trying to solve mysterious, weird wiggles in exoplanet spectra. So I hope that there is something hiding in the data, and if there is, we'll do the work to figure out what secrets are hiding in K2-18b's atmosphere. So ultimately, we just have to watch this space.
And so you mentioned, and of course, there are non-biological origins of DMS as well, because you can, I mean, it has been observed in comets, it has been observed non-biologically as well. So I'm curious, what kind of signatures would be sort of like, you would say, okay, well, here are the suite of molecules. So let's 2 or 3. I mean, I'm not talking about sort of like 18, which I think maybe sort of like, you would need a lot more, but 2 or 3 that might pique your interest, and you go like, what, this is now getting to a place where uh, if there is sort of like, a reasonable 5 sigma detection of 2 or 3 molecules which is piquing your interest in terms of life, what would those be?
So there are other molecules that have been considered to be possible biosignatures, like CS2 carbon disulfide, for example, which is not being seen at the moment in the current data. But of course, all this can change when you obtain more data sets and improve the precision. So I don't think any single gas will ever point towards the presence of life. We need to understand the context of the planet, what the actual nature of it is, and that requires getting data with multiple instruments across all wavelength regions, detailed interior modeling. So we need to understand the environment, and then you would want to see multiple gases, perhaps 2 or 3, that as far as we understand it, in that environment, cannot be produced with a significant amount abiotically. That would then start to kind of gradually convince people that this is a candidate planet for life. Um, and the term candidate would probably stick for quite some time. This is not just observations. We need to really understand this because this planet is so different than what we have in our own solar system that there's a lot of work that would need to be done to understand the context for what molecules can actually form without life. So we're just at the beginning of this journey. So there's not going to be a eureka moment tomorrow or a year from now. Haha, life proven. This is probably the journey of like a decade to really understand planets like K2-18b. And there are many other sub-Neptunes similarly that we can also study as well.
Well, that's great, and I think we are all on this journey. Everybody is excited about it, but I think a dose of sort of like reality and also skepticism, and it's crucial in terms of how to think about these things. So, Dr. MacDonald, thank you so much for your time and for your views on this and the context that you have provided. I really appreciate it.
Thank you for having me.
Thank you.